Good day to our virtual audience, wherever you may be in the world. It's my honor and pleasure to be presenting this tutorial at the PowerAfrica conference. And the title is System Operated Simulation Workshop. And my name is Robin Podmore. I am the president of Incremental Systems and also the honor to be a co-founder and senior vice president of IEEE Smart Village, and recently a president of a Rotary Club of Silicon Valley Smart Village. So what you're hearing today is mainly my focus on my primary job, which is working with simulators to train system operators throughout the world. So as we hear over and over again, our industry is going through great and rapid change. I won't dwell on all the different aspects, whether it's renewables, virtual power plants, extreme weather events, cyber physical breaches, and so on. But what we have today is some silos with communication barriers between the different groups that are responsible for operating and building energy management systems. And that's without even looking at all the other disciplines within a utility as you look at the different management groups. So these groups can be summarized as utility systems operators who are very familiar with preparing switching orders, often started their career in substations or power plants, and they're very used to running a mission critical real-time operation and working the switch work and having all working shift work and giving all the care and attention to being very precise in everything that they do, because lives are at stake, equipment is at stake, and of course, the consequences can be a major blackout affecting millions of people if there is an error. On the other hand, we also have utility operating engineers. They're running the power flow studies and the stability studies and coming up with the operating constraints in the daily plan. And then we have the application developers, those who know the internals of different applications, which sometimes are written in legacy codes and use the techniques like decoupled power flow and so on. And then, of course, we have the cyber defenders. They're familiar with Linux, JavaScript, cybersecurity, and they are keeping the computers running either hosted locally or more and more on the cloud. And so they have different backgrounds, and we need to have a more common language, and we need to have cross-training. So what we'll be presenting today is an operator training simulator, and we're encouraging people to be involved and to actually get their certification, and so that they go through the same simulator training that a real system operator has, and they actually come to classes virtually where they can actually be watching a real operator run a system under simulated environments, but where there may be major outages and even a restoration. So really what the industry needs right now is the ability to make power system analysis much simpler for everybody. One of the things that you noticed is as you get into an engineering degree, and maybe it's typically in your second year, you're starting to learn about how to use complex numbers to do circuit analysis, which has resistances and reactances and capacitances. And really at that point, it's not that appealing to a lot of folks. And really, you go all through that fairly laborious, detailed work, and it turns out when you become a power system engineer or even an operator, those calculations are really not useful at all on the job. Now, what we're proposing is that there's a need to run calculations from a spare tire EMS if your main software has a breach. So we've actually come up with some approaches to make calculations much, much simpler. Basically, we're saying let's use geographically based one-line diagrams and really key in on the line distances, and then create an electrical distance diagram that's all referenced to a single nominal voltage. So everything is normalized to a common voltage. It could be 230, it could be 345, but everything gets converted to that equivalent voltage. In the light text here, you can actually use those to calculate power transfer distribution factors and line outage distribution factors. But in today's session, we'll be mainly focusing on how to use those diagrams to calculate the voltage changing if there has been a reactor switched on or off, or a capacitor switched on and off. That's a very common thing that has to happen in normal operations as you go through daily load profiles. And we're saying, let's provide a simple way to make those calculations. And also, we have another module where you can actually see that when you add or subtract a reactive resource, like a capacitor or a reactor, we're able to figure out which generators on the network actually increase or decrease their megawatt output to support that reactive switch. So here's a preview of what you'll be looking at in this upcoming video on using electrical distance diagrams for voltage and megavar analysis. We'll be introducing a concept called TILA that looks about right, how to get something that is good enough for system operations. You'll be using the actual decoupled power flow techniques, but applying it to simple back of the envelope or calculator calculations. We will be introducing the whole idea of serial and parallel AC circuit calculations and reductions. For those who are a very strong power systems engineer, please forgive the fact that we're covering some very basic background, but those who are students or professors, please use these materials so that you can actually lay the foundation to make these calculations of networks very straightforward. And then you'll be looking at an electrical distance diagram where we take a real transmission system and we convert it to equivalent distances based upon different voltage levels. Then you'll be looking at voltage support diagrams, how to describe a diagram with all the generators that provide voltage and megawatt support for a given bus. And having voltage support diagrams is becoming more and more critical. We're replacing synchronous generators with renewable inverter-based devices, and they don't provide the level of voltage support and voltage strength that those synchronous machines really do provide. And then you'll go through some techniques to reduce diagrams to one equivalent generator, one capacitor, and from that equivalent, you can make the calculations of the impact of adding or deleting, adding or removing capacitors and reactors from the network, and how much will the voltage change.
Welcome, I'm Robin Podmore. The title of this module is Using Electrical Distance Diagrams for Voltage and Megavar Analysis. The terminal objectives for this session will be, firstly, to estimate the voltage change when a shunt capacitor is added to or removed from buses in the Cascadia system. Secondly, it's to estimate the megawatt changes that will occur on supporting generators when a shunt capacitor is added to or removed from the network. The enabling objectives will include developing an electrical distance diagram for the Cascadia network, and then developing a voltage support diagram that includes just those generators that support a bus with a shunt capacitor. Then we will develop an equivalent network where there's just a single generator bus and capacitor bus, and based upon that network we can estimate the voltage change when the capacitor is added or removed. In addition, we'll develop a network that shows how the supporting generators participate in supplying the megavars when a shunt capacitor is de-energized. Recurring theme throughout these modules is TILA. TILA stands for That Looks About Right. It's a term that is commonly used in the aerospace and airline industries for providing tools to operators or pilots so that they can make really good judgments in real time. There are times when being willing to approximate can be less risky than shooting for absolute precision. There's a saying that sometimes relates to engineers: analysis paralysis. And in a real-time system where you have to make decisions or there are very severe consequences, TLAR can be literally a life-saving technique. So to give you a preview of what we'll be covering is that we'll be using the Cascadia system, and we'll be using the distances of the actual transmission lines on this system. And we'll be normalizing everything in the system to the equivalent of a 230 kV transmission line. So when you see the numbers on this diagram, that means that that line there is equivalent to 16 miles of 230 kV. And this is the main concept. Normally when we think about power systems, we talk about the resistances, the reactances, the capacitances, and we actually can convert those to a per unit system. But those are very difficult things because they're not integers. They're difficult for an operator to actually use with a rule of thumb or calculate in real time. So what we're saying is, let's convert everything to the equivalent of a 230 kV single circuit transmission line. These are nice integer numbers. They're intuitive. You can verify from a map that what those numbers really are, and they really do get you in the ballpark or are a great way of doing TLAR calculations. So we'll be building an electrical distance diagram that really takes everything in the Cascadia system. It takes lines that are parallel and combines them into a shorter line. It takes 500 kV lines and makes those into shorter 230 kV lines. And it takes the transformer and moves those to an equivalent line length. And so that's what you're seeing here. In each side of these generators, we're showing you the actual equivalent line length of its step-up transformer. And then we take those values and we merge them with the actual values of the transmission lines themselves, and we build this, we call this the voltage support network. We only include those generators that are close electrically to the shunt capacitor that we're looking to remove or add, and we build this voltage support network, which you can see is a lot simpler than the real network. So once we have that voltage support network, we can apply some reduction techniques through series and parallel path combinations to reduce that network to where we have all the generators working in parallel through a single equivalent line to the capacitor. And then we can figure out the voltage drop on this bus if we remove the capacitor using the TLAR rule that 100 megavars over 100 miles of 230 kV gives a 13.5% voltage drop. The other thing that we can do is we can use that voltage support network and transform it into an equivalent network where each one of these generators is feeding the capacitor through a dedicated line, and the lines have different lengths. And what will happen is that if we trip this capacitor online, each one of these generators will pick up the megavars of that capacitor inversely proportional to the line length. So we call that the generator participation network. The NERC standards that are most appropriate to this whole module is TOP 010-1. The requirement of that standard is that the transmission operator shall have a process or procedure to address the quality of the real-time data, to perform real-time monitoring and assessments. Well, the rule of 100 megavars over 100 miles of 230 kV line gives a 13.5% voltage drop can be applied to real-time networks and validate that given the megavars traveling over a certain path, by figuring out the distance of that path in equivalent 230 kV line length, you can verify whether the voltage at the sending end and the receiving end is reasonable. TOP 01-1, requirement 3, says the TOP shall have operating processes and procedures to address the quality of analysis that are used in the real-time assessments. This primarily refers to the contingency analysis software. So the contingency analysis software is looking at all the different single contingencies and double contingencies and giving you voltages as well as line overload conditions. Well, the TLAR rule in this case can also be used to look at the post-contingency results. Are the voltage differences that you're getting from the contingency analysis reasonable compared to your TLAR calculations? This is very important for system operators to do. These new applications are relatively recent. They were motivated by the blackout in the Southwest in 2011, that every transmission operator had to run contingency analysis at least once every 30 minutes. You can have a modeling error, or you can have some bad data that will actually make those programs give results that are not realistic at all. We're giving you the analysis tools to make your own decisions about, is that a real violation or is it potentially due to bad data, without having to call in the operating engineer. So let's recap the TLAR equation for the voltage at the sending end of a transmission line that is connected to a generator that is regulating the voltage at that receiving end. So the path reactance is X, the angle between the buses is delta, the voltage at the receiving bus is VR, the voltage at the sending bus is VS. VS on is the sending bus voltage when the capacitor is in service. VS off is the sending bus voltage when the capacitor is out of service. The real-time reactive power at the sending end is QS, and the nominal megavar rating of the capacitor in per unit is QN. So if we are switching a capacitor in service, then the voltage with the capacitor on is the voltage with the capacitor off plus the nominal megavars of the capacitor bank times the reactance between the buses, and we also multiply it by the voltage with the capacitor on. We solve this equation iteratively. If there's a big increase in voltage, then we have to run this equation through a couple of times to get the final result. If we're taking the capacitor off, the voltage with it off is the voltage with it on minus the nominal MVR rating of the capacitor bank times the reactance times the voltage with it on. In this case, there's no need for any iterations because we know the voltage with it on, and we can always get our solution with it off in a single simple calculation. One of the techniques that we'll use in deriving and simplifying our voltage support diagrams is series and parallel circuits. The objective in this segment is to describe the principles for combining series and parallel elements with megavar flows in AC networks. To do this, we'll review series circuits in a DC network. In a series circuit, the exact same current is flowing through each of the resistances in series. The equivalent resistance around this loop is simply the sum of the individual resistances. So in this case, it's R1 plus R2 plus R3. The current in the network is the voltage across the battery divided by the sum of the resistances. The voltage drop across each one of these resistances will be proportional to the magnitude of that resistance. If we now look at a DC parallel circuit, then we have a different current that flows through each one of the resistances. The actual amount of the current will be proportional to the inverse of the resistance. So I1 will be the voltage divided by R1. I2 is the voltage divided by R2, and I3 is that same voltage divided by R3. So the summation of the currents is really the voltage divided by R1 plus the voltage divided by R2 plus the voltage divided by R3. So if we look at this equation here and we take the V and we put it outside of all the resistances, we have the voltage times the summation of the inverse of the resistances. And that is equal to the voltage divided by the equivalent resistance. So when we compare these two equations, we can eliminate the V from both equations. We can say 1 over R equals this value here. We simply eliminate the V from this side, the V from this side, and we conclude that 1 over R is the summation of the inverse of each resistance. So when we have parallel circuits, to get the effective resistance of all those circuits in parallel, we go through the following steps. We take the inverse of all the parallel resistances, we add those all together, we take the inverse of that resulting number, and that's the equivalent parallel resistance. And always we find that the effective parallel resistance has to be less than the smallest resistance in the whole network. So now let's look at how we adapt the series and parallel concepts in the DC networks to apply to an AC network. To do this, we'll use the decoupled power flow formulation. This was first published by Dr. Brian Stott in 1972. In this formulation, we consider two separate problems. We consider that the megawatt flows are dependent on the angle differences. And we consider that the megavar flows are dependent on the voltage magnitude differences. As power system operators, we talk about how megawatts flow downhill on the angle difference. We also talk about how megavars flow downhill on the voltage magnitude difference. So we've had the concepts around for a long time, but we really haven't followed through and provided you with the operating tools to put those concepts into practice and make quantitative assessments. By that I mean how much megawatts will flow on this path versus another path, or how much voltage magnitude difference is needed to support a megavar flow. In the voltage support networks that we'll be developing, we'll consider generators with dynamic megavar reserves as constant voltage sources. Those generators are holding those regulated voltages, which may be either on the low side or the high side, at a constant value as long as they are within their megavar limits. The megavar loads are modeled as extractions from the network. Shunt capacitors are modeled as megavar injections to the network, and shunt reactors are modeled as megavar extractions from the network. We calculate megavar flows based upon voltage magnitude differences and the path series reactance. In this analysis, we just consider the reactance, the series reactance of the lines and transformers, and we ignore the resistance elements. For transmission networks, the ratio of the reactances to the resistances is very large, typically 10 or greater. Let's look at a simple AC series circuit where we have a single generator regulating its receiving bus, and we have a single shunt capacitor producing megavars Q into a sending bus, and that reactive power is being transmitted over this set of transmission lines, each with reactances X1, X2, and X3, all in series. We will ignore the megavar losses in each reactance, as well as the shunt capacitance of the transmission lines for this simple analysis. So in this case, the same amount of reactive power Q flows through each of the elements. The equivalent series reactance is then just the sum of the individual reactances, X1 plus X2 plus X3. Our reactive power is our sending voltage minus our receiving voltage divided by the series reactance, X1 plus X2 plus X3. The voltage magnitude drop across each of those reactances will be proportional to the magnitude of that reactance. Basically, the reactance is going to increase with the line length. And so the longer the line, the more the voltage drop across that line. Let's now look at a parallel circuit for megavar flows in an AC network. In this case, a different megavar amount flows through each parallel reactance. In X1, the flow will be the voltage at the sending minus the voltage at the receiving end divided by X1. Q2 will be the same voltage across the path divided by X2, and Q3 will be the same voltage difference across the path divided by X3. If we sum these up, we get the total reactive power is the summation of the difference divided by the appropriate reactance. If we extract the common element of the sending minus the receiving voltage, we end up with this equation. The reactive power is the sending minus the receiving voltage times 1 over X1 plus 1 over X2 plus 1 over X3. And we can say that that is the sending minus receiving voltage divided by an equivalent reactance. If we cancel out this term, sending minus receiving voltage, on this equation, on this side, cancel out that term with that term, we get that the sum of the inverses of the reactances is the inverse of the equivalent reactance. What we do now is we multiply both sides of this equation by the reactance X. So this cancels out to give us 1, and on this side we get equivalent reactance times the summation of the individual reactances inverted. We then divide both sides of this equation by the value here in the parentheses, and we end up with our reactance equals, the equivalent reactance equals 1 divided by the summation of the inverse of the individual reactances. So the process to calculate the equivalent reactance is to take the inverse of all the parallel reactances, add them together, and take the inverse of the result. The equivalent parallel reactance has to be less than the smallest reactance in the combined path. Let's look at the case where we have an AC circuit with two parallel paths. We have a generator regulating its terminal bus at the receiving end. We have a capacitor at the sending end, and we have a flow Q1 and Q2 over those two parallel paths with a reactance of X1 and X2. This little case will come up over and over again as we're doing our calculations, so it makes the whole process quite simplified. So the inverse of our equivalent reactance is the summation of the inverse of the individual reactances. Let's take this equation and multiply it by the product X1 times X2. So we get x1 times x2 divided by the equivalent reactance equals x1 times x2 divided by x1, and then x1 times x2 divided by x2. The x1 terms cancel out right here, so this boils down to x2. The x2 terms cancel out right here, and this boils down to x1. Let's multiply both sides of this equation by x. We get x1 times x2 equals x1 plus x2 times x. Now let's flip the sides of the equation. This term comes over to the left-hand side. This term goes to the right-hand side. And then we divide both sides by x1 plus x2, and we get the resulting equation. X is x1 times x2 divided by x1 plus x2. That's a very simple equation to remember as you're doing your parallel path circuit reductions. It's quite simple to do with a calculator, and so basically that's the key to reducing a complex circuit down to one with just a single element, and you can do that on the fly without even having to use a spreadsheet. The next major topic is electrical distance diagrams. The objective of this segment is to derive an electrical distance diagram for the Cascadia system where the line lengths are based upon equivalent 230 kV single circuit lines. Here's a preview of the process. For all the cases where we have parallel lines, we'll convert them to an equivalent single line with a smaller length. We'll also convert the 500 kV lines to equivalent lines with a much reduced length. We'll then also convert a case where we may have a 500 kV line in parallel to a 230 kV line to an equivalent 230 kV line. And finally, we'll convert the transformers, both the bulk power step-down transformers from 500 to 230 kV and generator step-up transformers to equivalent 230 kV lines. Our goal is to preserve the network reactances between substations so that the megavar flow changes and the voltage magnitude changes in the equivalent network will be the same as in the original network. However, the equivalent network will be greatly simplified to enable manual calculations. So here is a geographic map of the Cascadia system with the lengths of the 500 kV lines and the 230 kV lines shown in miles. The magenta are the 115, and for our analysis they will not have a significant impact on our calculations. The Cascadia system has a common construction for all 230 kV lines and 500 kV lines. The reactance per mile for a 230 kV line is 0.00135 per unit. The reactance per mile for a 500 kV line is 0.0002 per unit. If we take the ratio, then the reactance of the 230 is 6.75 times the reactance of the 500 kV for each mile of length. The first step in the transformation is to take all the parallel 230 kV lines and reduce the length of the path by combining the lines in parallel. So the effective path length between Chehalis and Auburn, which has 4 lines in parallel and a length of 48, is really equivalent to a single line with 12 miles. So where we have 2 lines, we're reducing it by a factor of 2. 4 lines by a factor of 4, and 3 lines, it's by a factor of 3. And we're rounding the miles off to the nearest integer. So that's a fairly straightforward transformation. Now let's look at the 500 kV lines. We'll start out with just looking at those lines where we have a single circuit between 2 major substations. We'll defer on looking at the cases where we have a 500 kV line in parallel with a 230. We take the single circuit 500 kV lines, and we divide them by a factor of 6.75. So for example, the 75-mile line between Wenatchee and Elma is equivalent to 11 miles of 230 kV line, because we divide the 75 by 6.75. So we know that the electrical distance between two stations with a 500 kV line is much shorter than if that was a 230 kV line. So we're taking that concept that we often talk about and actually putting it in terms of numbers. In the case where we have a 500 kV line with one or more parallel 230 kV lines, then we simply divide by the 6.75 plus 1 if there's a single 230 in parallel, plus 2 if there's two 230s in parallel, and 3 if there's three 230s in parallel. The math for doing that is given on the right hand side here. I won't go through it, but those who want to see the proof can look at the equations here in detail. So let's look at the cases where here we clearly have a 230 in parallel from Yakima to Findlay. We have a 230 in parallel from Findlay to Walla Walla. And we have almost a 230 in parallel because we've got this line that goes from Walla Walla to Coyote Ridge to Pullman. And it's almost in parallel, even though it's being routed through this station. So in this case, we'll do the reduction by dividing by 7.75 miles. And we're taking the 75 and converting it to 10, the 33 to 4, and the 67 to 9. So in this version of the map, we've taken all three reductions together. We've taken the parallelization of the 230. We've taken the conversion of the single circuit 500s, and then we've taken the conversion of the single circuit 500s in parallel with the 230, and those are the results and the equivalent distances shown on this map. If you took our courses on managing transmission network flows, you'll recall that we did a very similar reduction or transformation for analyzing the megawatt flows. In this case, it's the exact same reduction, and we're applying it for megavar flows. Now, in the case of the Puget system, we have this path from Renton to Linwood that goes either through Renton to Seattle to Linwood, or Renton to Bellevue to Redmond to Linwood. And sometimes we want the effective length of the path all the way between Renton and Linwood directly. So again, this is the equivalent line length when we've done the parallel combination. So we had 15 with 3 lines in parallel, that converts to 5. We had an 8 with 3 lines in parallel, and we round that up to 3. But here we'll take the combination of this path in parallel with this path. First of all, we'll do the series combination of this path in series with this, and we get that the reactance from Renton to Seattle to Linwood is 8 miles, the 3 plus the 5. The second reactance from Renton to Bellevue to Redmond to Linwood is 11. The 4 plus the 3, which is 7, plus the 4, which is 11. Now we'll do our parallel combination. We've basically got a path of 8 around this way, 11 around this way, and the parallel path is the product of the two, the 8 times 11, divided by the summation, which is the 8 plus 11, and that comes to 4.63, or almost 5 miles. So you see how that very simple calculation can be applied to build a equivalent impedance or reactance for two parallel paths. And we've actually done the combination. We combined the paths in series around this way, in series around this way, and then we took those equivalent lengths and reduced them to a single length from here to here. So we show that on our final transform map of the electrical distance diagram. We have the white arrow. We have the white arrow that says the equivalent distance in miles from Renton to Linwood is 5. Now we also have to account for the impact of transformers. At Everett, we have a 500 to 230 kV transformer, and its reactance is 0.013. In working with the Cascadia system, it's important to remember that the reactance per mile from a 230 kV line is 0.00135. So if we convert that transformer to the equivalent miles of 230 kV, we take the 0.013 divided by 0.00135, and that is close to 11 miles of 230 kV line. The reactance of the Auburn 500 to 230 kV transformer is also 0.013 per unit. Again, the reactance per mile for a 230 kV line is 0.00135 per unit. So the Auburn transformer is equivalent to 9.63 miles, or approximately 10 miles of 230 kV line. Because we have two Auburn transformers in parallel, the parallel combination is equivalent to 5 miles of 230 kV line. Since we're regulating the low-side terminal buses, we have to include the generator step-up transformers in our calculations. We can find these values by clicking on the generator pop-up menu with the right mouse click. In this spreadsheet, we've gone through and we've calculated the equivalent miles for the different generator combinations throughout the Puget system. Where we have two generators in parallel, like at Everett, we take the impedance of each transformer and we combine it to an equivalent impedance, and then we divide that equivalent impedance by our 0.00135 impedance per mile for the 230 kV to get the equivalent miles. So for Everett, we have 11 miles for both generators in parallel. For Mount Vernon, we have 16 miles. For Renton, we have two parallel generators, each with impedance of 0.06, and that's equivalent to 22 miles. For Chehalis, which is a large unit, it's 0.01, the reactance, and that's 7 miles. And for Satsop, which are very large 1200 megawatt units, we have two very large generator step-up transformers, each of 0.013, and that combines to 5 equivalent miles. And we've got our bulk power transformers at Auburn that give us 5 equivalent miles. So depending upon where our capacitor is located, we'll be looking at various generating combinations as the supporting generators for that bus, and you'll have to include various amounts of their generator step-up reactance. So we have a generic equation that can be really useful, and that is when we look at the sending voltage minus the receiving voltage is the reactive power flow times the path reactance. So if we say the reactance for 100 miles of 230 kV is 0.00135 times 100, that's 0.135 per unit. If we say we're looking at 100 megavars, or 1 per unit of reactive power flow, then our sending minus receiving voltage is simply 1 times 0.135. In other words, if we move 100 megavars over 100 miles of 230 kV, we should expect a 13.5% drop in the voltage magnitude between the sending and the receiving end. This equation works very well for the Cascadia system. We suggest that you work with your transmission operating engineers and decide that before you apply to this system, you look at the typical reactance per mile of your actual circuits on your system to see if you can use the same value or you should use a modified value. The principles we cover here are applied to a combined 500 kV and 230 kV system, but the exact same principles can also be applied to systems with other voltage levels, for example, 345 kV, 765 kV, and 138 kV. In this next segment, we'll be building an equivalent circuit to study the outage of the Everett shunt capacitor. We'll have three objectives. We'll create a voltage support network with electrical distance diagrams to solve the outage of the Everett shunt capacitor banks. We'll reduce that electrical distance diagram to a single element to solve the voltage reduction when that shunt capacitor is removed from service. We'll also transform the voltage support network so that each supporting generator feeds the shunt capacitor through a dedicated line. We can then use this network to estimate how the supporting generators participate in providing megavars when the shunt capacitor is removed from service. So what you see here in the top left is what we call a voltage support network. We have identified all the generators that provide voltage support for the Everett bus. We know that at the airport generating station, the units are on their maximum megavar limit, so we're not including that station in this voltage support network. We've also done the analysis, and we've seen that the electrical distance from the Wenatchee station over in the Palouse side of the system is actually less than the electrical distance for the generators that we're showing here. So we start out and we assign a distance within each of our generators to represent the generator step-up transformers. So for Everett, it is 11 miles. For Mount Vernon, it is 16 miles. For Chehalis, it's 7 miles. For Satsop, for both units 1 and 2, it's 5 miles. And for Renton, for all 6 units, which are fed through 2 parallel transformers, it's 22 miles. We now look at the distance between that generator, the high side of the generator transformer, and the bus, which has the shunt capacitor. For Everett, the distance is 0 because the capacitor is located right at the Everett generating station. For Mount Vernon, the distance is 17 because to get from Mount Vernon, we have to go to Marysville, which is 15, and then to Everett, which is 2. So that's a combination of 17 miles to go from Mount Vernon to Everett. For Chehalis, we have to go 12 miles to Auburn. And so we notice that Satsop also feeds into the Auburn station. So when we have a station which is fed by multiple supporting generators, we have to model that explicitly in our network. For the Sapsop unit, we go through 4 miles, which is the equivalent of the 500 kV, and then we have to go through 5 miles to go from the 500 kV bus to the 230 kV bus. That 5 miles is those two 500 to 230 kV transformers working in parallel. And then from the Auburn 230, we come on up to Renton. Renton is also another generator feeding the system, so we have to model the merging of the path from Renton along with the path from Auburn. So the path from Auburn is 5, the 2 plus 2 plus the 1, to the 230 kV. The distance from the Renton high side bus is 0, so there's no mileage required there. And then to go from Renton to Everett, we've got 7 miles, and that represents the 5 miles of this equivalent circuit. Remember, we built an equivalent circuit of 5 miles, which represents the path around this side, from Renton to Seattle to Linwood, and from Renton to Bellevue to Redmond to Linwood. All of that is 5 miles. So now you're seeing we've got 5 miles from Renton, jumping all the way to Linwood, and another 2 miles, so that gives us 7 miles here. So this is a very simplified but very insightful voltage support network that can model what happens in the Cascadia system. In this diagram, our goal is to take the voltage support diagram that we just developed for an outage of the Everett shunt capacitor and transform it into this simple diagram at the bottom right here, where we have all the generation running in parallel with a single 5.3 mile line to the shunt capacitor at Everett. So each of these arrows indicates a transformation. We have one here, and then we come from this circuit up to here, and then we transform to this circuit, and then to this circuit. So let's just go through each of the steps. In this step, we're simply taking the equivalent distance of the generator step-up transformer and making it explicit on a path. Or we're combining the generator step-up transformer with the path distance. So here we have 16 plus 17 gives us the 33. For Chehalis, the transformer is 7, the path is 12, it becomes 19. For Satsop, the generator step-up transformer is 5. We combine it with the 4 for the 500 kV line to Auburn, and then we've got the 2 transformers in Auburn from the 500 to 230 kV line level. So the 5 plus the 4 plus the 5 gives us 14. And then for Renton, we're taking the 2 generator step-up transformers and making that explicit on this path here. The next step is to do a parallel combination. We have Chehalis and Satsop both feeding the Auburn 230 kV bus in parallel. So we do our parallel combination. We multiply the reactance of path 1 times path 2, the 19 plus the 14, and we divide it by the summation of the reactances, and we get an equivalent path length of 8. So we put the 8 in here to represent the combination of the 2 paths from Chehalis to Auburn 230 and Satsop to Auburn 230. Now as we transform to this equivalent circuit, what we're doing is we're taking the 13 miles of this path here, the 8 plus the 5 plus the 22, and combining those in parallel. So we have the 13 times the 22 divided by the 13 plus the 22, and that gives us 8. So the combination of this path in parallel with this path is 8 miles. You can see the power of this simple equation for combining parallel powers when we just have the 2 circuits. So we're now down to the combination of Chehalis, Satsop, and Renton 1 through 6 are feeding into the Everett bus through an 8 plus a 7 mile equivalent path. We combine those simply into 15 miles. And now for the final conversion, we want to take these 3 parallel paths and combine them in parallel. We could do it with a calculator, but to make it simpler, we've put it into a spreadsheet where we take the 11, the 33, the 15, do the inverse, calculate the summation of all those inverses, and then do the inverse of the final product. And we get an equivalent path of 5.32 miles. So to summarize, we've taken the actual Cascadia system diagram, simplified it to a voltage support diagram, and then converted that voltage support diagram to an equivalent system with all our generators running in parallel across a single path to our shunt capacitor.
Well, welcome back. We hope that that whole module gave you a good introduction on how we can make some very straightforward calculations and calculate the change in voltage as we add and take off reactors and capacitors. We'll be getting into some simulations a little bit later, and we'll put those simple calculations to the test on a fairly complicated model. Now, before that, I'd also like you to look at this video, which looks at how we can calculate how various generators will participate in providing megawires to support both reactive and capacitive switching. Again, we'll have an electrical distance basis to build a voltage support diagram. And you'll get the equivalent distance between each supporting generator and the bus, where you'll have either the capacitor or the reactive switching. Now, as part of this, you'll be seeing the use of a technique called parallel path expansion. Normally, we take multiple parallel impedances and we combine them into a single equivalent. In this case, to get an independent calculation, we actually take a single impedance and we break it into a number of parallel paths so that each generator has a separate parallel path directly from the generator to the regulated bus, well, to the bus with the capacitor or reactor. And that's the foundation to really quickly see which generators will provide the most megawire support to an event on that bus. The support basically comes from the generators that have the shortest electrical distance to the bus where the capacitor or reactor will be switched.
In this exercise, our goal is to develop a network that shows how the different generators will participate if there is an outage of the Everett capacitors. Previously, we showed you the technique of doing a parallel path reduction. We showed you how we could take the path of 19 here and 14 here and combine that and reduce it to a single path. In this case, we have to do the reverse. We have to do a parallel path expansion. We have to take the link which has got the common flows of Chehalis and Satsop and expand that into two separate links which have the individual flows of both those generators. So let's look at the process to do that. We'll call this path here path A and this path here path B. And so we document the miles on path A, and we take the inverse of the miles on path A, and then we take the relative path admittance. In other words, that's the ease of flow on those two paths. And then we take the miles on the common path of 5, and we go through the transformation. We divide the miles of the common path by the relative path admittance, and we get this factor 12 for path B on the Chehalis generator. So that's the 12 here. And the 9 for the path B on the Satsop generators. That's the 9 here. And by doing this transformation, we've literally preserved the total reactance through this path. If we did and checked and did the combined parallel path combination here, we would get this reduced down to the original 5. And what we've also done is we've made sure that the impedance of this element divided by this element is the same as this element divided by this element. So we've kept the same ratio of the distance on this path and this path as we have on this path and this path. So let's do the same transformation for path C, which has a length of 7 miles. Again, we take the miles of path A and B in this case, which is 19 plus 12, 31, 14 plus 9 is 23, and then the 22. We take the inverse of those path miles, we sum the inverse, and then we take the relative path admittance. This relative path admittance is simply these same numbers, but scaled so that they'll add up to unity. We then take the miles of the common path and we divide it by this relative path admittance to get 26, 20, and 19, and those become the path lengths that we put in here, 26, 20, and 19. And again, if we did combine these all in parallel, we would end up with a path length of 7. And again, the ratio of these values here of path C to the length of path A and B is all consistent between all three legs of this circuit. So in the final step, we simply do the combination. The 19 plus 12 plus 26 gives us 57. The 14 plus 9 plus 20 gives us the 43. And the 22 plus 19 gives us the 41. And so if we take those numbers across here, the same path lengths, and we take the inverse of those path lengths, and we sum them up, and then we scale those numbers so that they all come to unity. This is the estimated participation of the megavar flows in each of those paths for the loss of this shunt capacitor. If we actually take the measured megavar increase of those generators, when we remove that shunt capacitor, that's the numbers that we have down here. And the measured participation is the proportion. In that case, each of these generators responded for a total of 81 megavars. And if we take the proportion, this is the measured participation, and we can see that this measured participation agrees quite closely with the estimated participation as shown here. So this is a very powerful and easily updated tool. If, for example, our Renton units were offline and our SATSOP units were offline, there'd be no path sharing. In that case, my relative length for Chehalis would simply be the 19 plus the 5 plus the 7. And so I can very easily update these diagrams depending upon which generators are in service or which generators are hitting their megavar limits. So this module has introduced some new tools and concepts for manually calculating voltage differences that are required to support megavar flows in AC networks. They can be applied to an existing system where the base voltages and megawatt flows are known, and an operator desires to estimate the change in voltage in magnitude that will occur from adding or removing a shunt capacitor. They can also be used to estimate the participation of other generators in the megavar flows when shunt capacitors are removed from or added to a network. So even though large-scale power flow programs are more commonly available, a manual tool really still has advantages. It can be adapted to any power system configuration. It is especially useful during restoration scenarios. Conventional tools like state estimator and contingency analysis are often overloaded and will not converge under such situations. It can be used to detect errors in power system parameters. Clearly, it's not vulnerable to cyber attacks because basically you're running with maps of your system and an Excel calculator. And it does provide a much greater degree of insight into power system VAR resources and bus strengths compared to just running the power flow. And especially when you use the two together. When you do the calculations using the TLAR equations and the electrical distance diagrams, and you go check with the power flow how the two agree, you build a really good understanding of what's happening on your system. And finally, it's a good tool for suggesting where corrective actions could be taken to increase or decrease bus voltages. Let's summarize what we've accomplished in this module. We started out and developed an electrical distance diagram for the Cascadia network. All the lines of different voltage levels, 500, 230 kV, were transformed to an equivalent single circuit 230 kV line distance. We then showed how to develop a voltage support diagram that just includes the generators that support a bus with a shunt capacitor. We then showed how we could build an equivalent network and reduce that to a simple network with just one generator bus, one capacitor bus, and one transmission line. From that equivalent network, we were able to accurately estimate the voltage change when a shunt capacitor at Everett was removed from the network, and we verified using Power Simulator that the estimated results agreed very closely with the measured results. We then developed a network that shows how supporting generators participate in supplying the megavars when a shunt capacitor is de-energized. We then compared the results with the power simulator to show that the estimated results are then agreed very closely with the results obtained with the simulator.
So welcome back from the video on how to calculate the allocation of megavars when a capacitor or reactor is switched to the various generators that are supporting that bus in the network. What we'd like to do now is to actually go through some demonstrations on this hypothetical Cascadian network, which has been developed specifically to training power system operators. And it's layered on top of the geography of Washington State. And the system has a 500 kV backbone in the red, along with the cyan or blue 230 kV. And as we saw in the previous module, we went through and we converted that to where we had these equivalent 230 kV line lengths, or the electrical distance diagram. So what we'll do is we'll be running the simulator and we'll be looking at the impact of switching a shunt reactor at this station in Elma and also at this station in Walla Walla. These are all hypothetical substations. The places are real, but the equipment and the configuration is not based upon any specific company data. The individual generators and transformers do have typical parameters of real 500 and 230 kV equipment. So we'll get involved with the actual simulator, where we have we're actually running in real time right now, and we can open up a actual real-time system map. Here's one that does have the exact same geography that we've talked about, and we'll actually be zooming in and we'll be looking at what's happening at the Elma station. The Elma station actually has 10 hydro units of 100 megawatts apiece, and it has a 150 megawatt shunt reactor. The other station we'll be looking at operating a reactor is at Walla Walla. And at that station, we have some wind turbines that are all offline. These units are all relatively small, about 16 megawatts. But there is a reactor there, a fairly large one, of 250 megavars. So the question is, if I switch these reactors in or out of service, what sort of voltage can I expect to see change at that substation? The voltages are actually shown so that if it's nominal, we've got 50% orange, 50% yellow, 50% blue. When the voltage goes high, at 105, it goes all yellow. Goes low, it goes all blue. So it's analogous to someone in the water with a scuba mask. As they go up, they see more yellow. As they go down, they see more blue. So this gives a very nice graphical way of seeing the voltages in the system. Everything's within a nice 95 to 105% range right now. So to apply the electrical distance diagram to this situation, we've got to know which generators will supply supporting megavars. Now, in the case of Elma, that it has support coming from Liberty over here, and it will have support from Wenatchee. Those are pretty much the closest large generating units in the neighborhood of electrically close to Elma. And really, in this case, we believe we can get a pretty good approximation by looking at, if I add a reactor here, I will get support from the Elma units, the Wenatchee units, and the Liberty units. On the other hand, if we add a reactor at Walla Walla, we'll get support from Liberty. But all these units are off. Take a look. We have some combustion turbines at Finley, but they are all offline. The breakers are open. We have 2 large solar units, power plants of 250 megawatts each at Yakima, but they're offline. The breakers are open. So we're coming all the way over to Satsop, where we have 2 very large nuclear units of 1,200 megawatts each. And so those will provide the support for reactive switching at Walla Walla. We'll get some support from down at this large coal plant at Chehalis, but really most, I think, to get a good approximation, we'll just consider those 2 sources. So let's go through and actually run through the calculations. Let's calculate the important electrical distances for the Elma station and at the 500 kV bus. Here's the bus here. We want to look at the impact of switching this reactor into service. Right now we're at 528 kV. And if we close it, we drop to 522. We're getting a 6 kV drop from that. Obviously, if we have a real-time simulator, this is, we don't need to do calculations, all right? But let's imagine we don't have the real-time simulator. But what we do is we have the drawings, all right, of this station. We've got a 1-line diagrams in a static form. So what we have to realize then is that this bus at here is supported locally through these 2 transformers in parallel. And then we've got these 5 transformers, each with 2 generating units attached. So what we have to do for the electrical distances, we have to take the actual reactance of that transformer, which is 0.01295, and divide it by 0.00135. That's the reactance of 1 mile of 230 kV transmission. The other thing we have to do for these transformers is we've got to take their reactance of 0.06 and divide it by 0.00135 and get the equivalent length in miles, and then divide that length by all 5, because we've got these working in parallel. And then because the reactance is attached directly, the reactor to this bus, there's no transmission line distance in this particular case. So for Alma, the numbers we get for the 2 500 to 230 kV transformers is 4.7 miles, and the number we get for the 5 step-up transformers is 8.8, giving a total of 13.5 miles. Now let's come over and look at the support we'll get from the Wenatchee generating station. So Wenatchee is connected by this 500 kV transmission line, and that has an equivalent length of 11 miles. And then at the Wenatchee station itself, we've got a 500 to 230 kV transformer. So we take the value of 0.011 and we divide it by the 0.00135 to get miles, and then we divide that in 2 because we've got 2 of these in parallel. Now, in the case of the generators at Wenatchee, we've actually got 10 of them, each of 100 megawatts each. And this has actually got a 3-winding transformer. And that is got a reactance of 0.187. Now, that 3-winding transformer has actually been converted from a delta to a star configuration. And when you do that, you actually get a negative on the on this third winding. And because that's common, then we actually take the 0.18 and discount it with a negative by twice to 0.14 and convert that to miles, and then divide all that by the 5, because these are all working in parallel. And so that's the process that you see over here. In Wenatchee, we've got the length of the line, the length of the bulk 500 to 230 transformers, and the generator step-up transformers, giving us a total of 25. Now we're also getting, in this case, support from the Liberty unit. And so let's come on back to the Liberty unit, and we will see that Liberty is located over to the east. And when we take a look at Liberty, that's got 2 transformers. This is a very large 1200 megawatt coal unit. And we take that 1 transformer, which is 0.011, and again, divide that by the 0.00135. So, and then divide that result by 2, and we get the equivalent length of these step-up transformers. So that's the generator step-up transformer equivalent length at Liberty. That's the actual length of the Rockford to Liberty line, converted to a 230 kV basis. And then this is the length of the 4 parallel lines at 230 into Rockford, and that gives us a 19. So what we simply do is we take these 2 lines, equivalent lines in parallel, go through the parallel reduction, and we get almost 9 miles. And then we take this one and do the parallel reduction again, or combination with the 19, and we get down to 6. So we're saying the equivalent distance from the 500 kV bus at Elma, in terms of the parallel support that it's getting from all the generators here, and the generators here, is 6 miles. All right, so let's take those calculations and see what happens when we compare the TLAR estimates with the actual operations from switching on the power simulator. If we take Elma, we're starting out at 528.7 kV, and we put the reactor in service, and we end up with 522.5. Let's just summarize the calculation. We start with 528.7, we end up with 522.5. We measure a drop of 6.2 kV. From the TLAR calculation, we got an electrical distance of 6, which was predicting 6.4 kV. Given the complexity of the system that you've seen, that is a very good TLAR estimate. Let's come on to the other side of the system at Walla Walla. And before we do that switching, we'll take this reactor off. In this case, we're starting with 536.9 kV, and we put the reactor in service, 250 megavars, and we drop all the way down to 514.9. So that's the summary here, 536.9 all the way down to 514.9 for a 22 kV drop. And the TLAR estimate we got from a distance of 13.7, and then with 250 megavars, which is 2.5 per unit, we're predicting 24.1. And again, given the complexity of the system, that is a very good estimate. So we've shown that the whole concept of electrical distances is you can take a very complicated network that's very realistic, and by looking at the generators that are supporting each bus in the network, you can come up with very simple electrical distances that can give you very good approximations of the voltage changes. So in summary, we've shown you a very straightforward technique with the concept of electrical distances. And as we're obviously more and more systems are putting in energy management systems with contingency analysis. But again, it's not just a matter of if they're going to fail, it's just a matter of when, because a data error can cause a failure, a communications link can cause a failure, and also obviously a cyber attack can cause those applications to not be available. And so when we have this whole environment where we're so dependent upon applications and data can actually cause those applications to diverge, or even when everything is running perfectly well and your contingency analysis is predicting, say, a voltage collapse, it's really good to have other tools where you can independently make the calculations to verify that your applications are really giving you something that is a very realistic prediction of what could happen in the future. And this is really just the start of this whole effort. We have other techniques that can also show you how to manually calculate voltage stability limits as well as angle stability limits, but that will come in a future presentation. So thank you very much for your attention.